All right, we are in section 6.7 of the chapter 6, exponentials and logarithm functions, and we're going to stop at 6.7. There are other models in 6.8 and 6.9, and honestly, some of these other models might be more interesting to some of you guys, I don't know, biology or exponential growth or something like that. Decay, radioactive decay, things like that are in the book. But I choose to do 6.7 because it touches all the bases. In other words, it covers all of the stuff that we would need. These just get kind of specialized. And my goal really is to continue talking about exponential and logarithm functions, not to cover every possible model that uses those. So for an educational standpoint, I just like this section best because it just has so many things in it. All right, so you can look up the objectives. I'm going to read them to you, but the objectives of this section. But let's go through some formulas. And the book starts off with this formula, super easy formula. I mean, all it involves is multiplication. And they tell you, the interest you make in dollars is the principal you invest in dollars, the rate as a decimal. So in other words, if it says 8%, you would put the rate as a decimal. And then the time, typically in years, I say typically, the rate has a time element in it. So if the rate is 8% per year, then the time would have to be in years. So the time has to agree with the rate. We're going to find out that this is ridiculously oversimplified. For some strange reason, all math books give you this formula instead of this formula, A equals P plus PRT. And I don't expect you to see it right away, but I do want to break this down as to what the difference between this formula here is and those same letters in this formula. Well, basically, if you have a savings account that pays simple interest, A is the amount of money in the account, P is the amount of money you put into the account, and this is the interest in dollars. So just to oversimplify things, let's say you put $1,000 in, and a year later you were given $100 in interest, you would add those together, and that would be called your amount. And I could even factor this P parentheses 1 plus RT. Reason why I'm doing this is every formula we're going to see, every single one, every formula we're going to see is going to be solved for A, not for the amount of money, not for the interest. This is the only formula that just kind of is presented to us not from the standpoint of how much money we have, the amount, but just the amount of increase. And I think they do it because they just want the formula to be simple, even though this would be the simplest formula, in the book as well. But either formula gets you the answer. If they ask you how much money you made, that's the answer. If they ask you how much money you have, don't forget to add the initial amount you put in. All right. They don't stay on that one very long because they're already going to this idea of compound interest. So simple interest is just you're paid once at the very end of whatever the pay period is. That's not what this is. We're about to talk about compound interest. You just have to know these phrases. Annually is once per year, semi-annually twice, quarterly 4 times. Those are pretty obvious. There's also continuous, which would be infinite times a year, but we'll get to that. Oh, by the way, I know some of you are looking on YouTube and other places. There are a few books that will use 360 instead of 365 for daily. Our book takes daily literally one day, once a year, so 365. That might make a difference. Probably not, but it might make a difference in like certain decimal places. So don't use, if you see that tip elsewhere, don't use 365 for anything in our book, our website. All right. So a lot of words being thrown around here. Interest is the money you're making. Principal plus interest is what they're talking about. Principal is how much you put in the account, or in the case of a loan, how much you borrowed. But here it is. Compound interest is when the money is deposited or mathematically deposited, and that small deposit starts making money. So compound interest is the interest is also making money, getting interest. All right. I won't go over this one. It's really pretty straightforward. They calculate the interest by substituting these values. Like I said, rate has to be as a decimal, and time has to agree with the rate, but a very straightforward formula. Oh, they're going through, I won't go through this one. What they're doing is they're doing a problem by cyclically recalculating. I would have deleted this one if I had thought of it. We don't have anything quite like this. What they're doing is taking a snapshot every quarter and hand calculating what would happen if your interest was compounded. The reason why it's not much of a very good example is we have a formula that does that in one calculation. So yeah, you could calculate these things by hand without knowing these formulas, but yeah, why put yourself through that? All right, so here's a question. You have $2,000 to invest, so that's your P. The rate is given as a percentage, but you have to write it as a decimal. And they tell you how it's compounded, and we want to run these calculations through the formula here, through this formula. And every time it's going to give you the amount of money you have at the end of, in this case, the year. So if it's compounded one time and you're only doing this once for the year, you're actually going to see that formula. What you might notice, I don't even know if I like this example that much, because it kind of teaches us something. It's not that N is one that I have a problem with. T being one, you can't see it. There would normally be a T right here, R times T, but T is 1. So, all right, just keep that in mind. All right, so they multiply this out and they get the amount of money you get, the original $2,000 plus interest. Now, what if it's compounded semi-annually? Well, what that means is after 6 months, you get, how much you have it originally. After 6 months, you get a deposit of interest. It would be exactly half of what you got here, so $80 would go in there. And then for the next 6 months, both of these, your new amount of money, $2,080, will be earning interest. So that little extra $80 is earning interest all this time for 6 extra months. All right. How much interest? Well, apparently an extra $3.20 interest. So getting paid in the middle, getting paid after halfway into this. And again, this is just a mathematical, when I say getting paid, the money doesn't actually have to show up at 6 months. These are more mathematical concepts than literal concepts. But if they say, and I'll explain why I'm saying that, but if they say you're paid semi-annually, You might not literally see it until the end of the calculation, but you would have this much money. An extra $3.20 versus not being paid. And again, can you see the invisible t in this formula? There's normally a t right here. Sorry. The formula is P1 plus R over N to the N times T. But again, what I'm a little concerned about is this example has T as a 1, and some students might kind of miss that if they're using this example to do a problem where T was something other than 1. All right, so sometimes, if T were 10 years or something, you might be raising this, well, you would be raising this to the 20th power. There's also a, no, that's it. No, T only occurs in the formula one time, but T can really change things. I mean, in my opinion, none of these should be 1 in a good example, because 1s become invisible when you substitute them. But all right, it's the same thing going on all of these. Anyway, quarterly, T is 1. All right, run that calculation, and it's a little more money. I think it was 3. Well, let's see, it was 3. It ended with 320. Now it's 468. So a little more money, a little more money. When you're compounded. Now, we don't say paid, because you're not going to literally be paid every day, 365 days a year, but you can invest in something where they compound it daily, and it gives you a little bit more money. Now, here's the thing. We're about to talk about these same numbers, and keep this number in mind. Actually, keep this number in mind, 166.57. All right? Keep this in mind. We're going to recalculate this. How can what's better than interest compounding daily? Well, we'll get to that. But there is still the more compoundings, the more money you make. Daily is kind of the best there is, but there's one more called compounded continuously. And it's not going to give you much money over the course of a year. I'll only give you 1 more cent in this example. But I'll get to that. So let's talk about compounding continuously. So we have this formula, and it's a nice formula, and it's kind of why it's here. It's got E in it. It's got exponents. It's got a lot to it. In a way, it's a simpler formula than the one I had before, which I just wrote here. The formula for compounding not continuously, but the regular compounding formula for n times a year is this. And the reason why I put some of it in red and some of it in green is, notice that this has a P, an R, and a T. It has a P, an R, and a T. But this structure, this parentheses and this 1 and this n in the denominator, this n over here, gets replaced essentially with E. And the theory behind that, or the reasoning behind that, is E is one of those numbers. It's a number. There's only 2 numbers that have this, I would describe this way, E and pi. It's a number that you really can't describe with a calculation. You really can't describe it with a number. I can't say E is the square root of 9 or, 8 or something like that. There's no way to describe it other than with some kind of more complicated formula. And what's our formula? Yeah. As n approaches infinity, now normally you might see a 1 right here, but this parenthesis 1 plus x over n to the n is equal to e to the x. So all of this structure gets replaced, but the x gets carried out to each side. Now you don't need to know this, but just trying to make a connection between this formula and this formula. What happened is n got so big it maxed out of the formula, and we have this nice new formula. So same idea, same parameters as before. P is still 100, R is still 0.8, t is 1. So you substitute that into this formula. Use your calculator with the E button, and notice what you get. You get 1 penny more over the course of a year. Okay, not a big deal, but the calculation was easier than the calculation with than this formula with the number 365, the fraction divided by 365, raising to the 365. And I would say it's even a better formula when t isn't 1. So in other words, if t were 10 instead of 1, you'd be raising this to the 3,650. Your calculator might not even let you do that. Formulas like this are very complicated, and this is just a nicer formula. And it gives you a little bit more money. All right. The one thing I will say on the homework, sometimes students get a little upset because the computer does insist that they, calculate to the nearest penny. That has to happen because sometimes you are asked questions where you want to compare, compounding continuously to compounding daily, and the difference is just a penny. Is it just a penny? Let's see, 56. Did I see 66 here? Oh, 57. Yeah. Okay. Yeah, it is. Thought for a second there it was a little higher. Okay, no. Just a penny difference between the answer to one question and the answer to another. So what's going to happen if you type in for, this question, this answer, the computer's going to mark it wrong. Well, you probably already know that, but just so you understand, there's a reason why it would mark it wrong in this case, because, it would assume you used the wrong formula. All right, these formulas, anytime you have a formula with this many variables in it, you can solve for something else. In other words, most of them started with A equals ... right? But who says you have to solve for amount? You can think of something else. So the effective rate of interest, these formulas, by the way, I'm just going to have you write them down. They are what I call reference formulas, or maybe open book formulas. Feel free to write them down. On an in-class exam, I don't think any instructor would expect you to just have these at your disposal. Unlike this one, this formula. This is a formula that you should memorize for future math classes. All right. These formulas, pretty obscure, open book only. But let's see how they're using it. So they want you to make this comparison. I'll run through the numbers in this next section. So they're asking you to find the effective interest rate, right, through these scenarios. And they're just substituting the values into this formula. And remember what basically what you want to know is, how do these nominal, they sometimes call them, interest rates compare when, one's compounded monthly, one's compounded quarterly, one's compounded daily. Yeah. So compounded monthly, compounded quarterly, compounded daily. And that's really the only difference in all of these. Just substitute those in with the percentage rate as a decimal that they gave you each time. And now we're comparing real interest rates. The larger one is going to be the better deal. Okay, so First Internet Bank. Oh, I didn't answer the question. Oh, yeah. So this one, yeah, it's really close. I mean, these are so close, I probably wouldn't even walk across the street to get this deal because they're so close. But mathematically speaking, you can now compare them. All right, pretty straightforward calculation. Just the formulas are a little generally not memorized by most people, but it's just kind of a nice thing we can do with all of this math. Present value formulas. So now notice we're putting the A here, the amount of money. A is the amount of money after a certain amount of time. We're essentially solving for P. So a little switch happened, and the other change was the negative exponents. So with these formulas, again, I would almost consider these probably not the type of formulas people memorize, but in an open book environment, I think it's good. I didn't want to run through those formulas with this example. So a zero coupon bond means you don't get any interest paid, but it's worth a certain amount of money in 10 years. So, well, it doesn't have to be 10, but they're saying in 10 years, it's worth $1,000. So the question is, you have a certain amount of money, and in 10 years, it's going to be worth $1,000. Well, what's it worth now? So what would you be willing to pay now for $1,000 10 years from now? Well, this isn't just a feeling. This isn't just, well, I feel like I'd pay $500. No. The idea is you have to compare it to putting your money away compounded monthly. Let's say you did pay $500. And instead of doing this deal where you just doubled your money in 10 years, you put it away at 7% compounded monthly, or you put it away at 6% compounded continuously. If you wanted to make that comparison, you could make the comparison side by side, but you could just use this formula, these formulas, and calculate to the penny how much you should be willing to pay for the opportunity to get $1,000 under these conditions. So what is it worth if you insist on a return equivalent to 7% compounded monthly? This is how much money you should be willing to pay to get that $1,000 in 10 years. Now they said try it at 6% compounded continuously. So 6% is a lower interest rate, but if you want 6% compounded continuously, you'd use this formula, and you'd find that you should pay $5,048, right? In order to get a 6% return on your money. So that's those ideas. I want to get to probably the most common type of question in this section, and that is, using these formulas to calculate what we call doubling time. So let's look at an example, but they want you to find the rate of interest compounded daily to double your money. And here's the trick you need to know. So we're going to use the same formulas we had before, but doubling means the amount is going to double, right? The amount is doubled. So what we're going to do is we're going to replace, in this case, A gets replaced with something P, and P gets replaced with 2P. By the way, you can replace this with anything. I mean, since the letter is going to cancel, some people might tell you to replace A with $1 and replace P with $2, because that's essentially, when I divide by P, that's essentially what's going to happen. But when you see double, you want double on one side and single on the other. This, by the way, would have worked if, like I said, if we had left that at A and changed this to 2A, that would have worked as well. But run that through the calculation. Make sure you understand how to solve for R in this situation. It's pretty straightforward. They left out a step, I think. I would have taken the 7th root of both sides. right? And that's solved for this argument here. Then what? Well, we're going to subtract 1 from both sides. Well, when they turned it around. Subtract 1 from both, run it through a calculator, and you get this rate. Now, what's the rate, right? As a percentage, it would be 10.408%, or 10.41% if you round it off. So remember, R in all of our calculations is a decimal. Usually when we verbally talk about it, it's a percentage. How long will it take for your money to double or triple in value, given certain conditions? Again, we're going to start with our regular formula, depending on what we're talking about, if it's continuous, this formula. But notice how A is being replaced with 2P, because P is how much you invested, so 2P is double how much you invested. So this little trick right here it slows a lot of students down. Anyhow, divide both sides by P and you get a formula that's very easy to solve. Here they took log of both sides. You get the idea, all right? Found the calculation. This is years. This is how long it took, 11.55 years. I don't know why they said about 12. 11.55 would be what we calculated. It's dangerous to think in terms of rounding that off. Computer's going to want this answer, the answer you get from running through that calculation. That was doubling time. If they had said tripling time, this would have been, you would have replaced A with 3 times the principal. If they said quadrupling time, 4 times, you get the idea. They did the same, actually did it here. So tripling time, 18.3 years. I just want to say this little trick is also done with the other formula. If they ask the tripling time, not compounded continuously, but compounded annually, substitute into this formula. Right? Substitute here, but the trick is still you'd replace P with, or A with 2P for doubling time. Solve for T, if you're solving for time, and 3P for tripling time. And it would be very close to these, but the calculation would be a little bit longer. And the change might be so subtle that you might need more decimal places to distinguish one from the other. So obviously look at the website and see what they're asking for those particular problems. But hopefully you understand why I picked this section. You won't understand why I chose to skip section 6.8 and 6.9 after doing this section. But this section has so much in it with, E and logarithms. It really does cover the entire lesson of exponents and logarithms to be enough for the applications of exponents and logarithms. So that is 6.7.